Today, this afternoon, we're going to talk about concave and convex functions. Very interesting. Well, we haven't really talked about concave functions in much depth. Okay. So, let me begin by just repeating what's in your textbook. If you turn to page 322 and you look at equation 1120, I'll write it down here in case any of you don't have your books. But you don't have to write this down. This is equation 1120 on page 322. Lynn, is that satisfactory? It's light. Okay. All right. I'll try to be a little bolder. I don't know. I'm using this Office Depot one. Maybe the Expo one will work better. Let's see. Yeah. Okay. I'll try to push hard. All right. So here is the equation. And I'll just read what's in the book. A function f is concave if and only if for any pair of distinct points u and v in the domain of f and for theta between 0 and 1, the following holds. Theta times f of u. That's not very, I don't know. Let me try this one. Theta times f of u. Oh, that looks a little better. Plus 1 minus theta f of v. Is less than or equal to this. F evaluated at this point right here. Theta u plus 1 minus theta v. Okay. This has the interpretation of being just the height of the line segment connecting the 2 points. Okay, so this part right here is just the height of the line segment. This is just the height of the function, or the book calls it the height of the arc. Let me draw a picture to illustrate this. A typical concave function would look something like this. Here, we're assuming that y is a function of x, a single variable. So f of x, or y, is measured on the vertical axis. And a typical concave function would look like this. Now you pick any 2 points, u and v, any 2 values of x, any 2, and connect them with a straight line. Let's call this M, call this point N. Connect them with a straight line, and the straight line always has to lie on or below the function. Now this is our point u. This is our u value for x. Okay. The height of this would be f of u. Here's our v. Here's f of v. Now theta, where theta is some number between, any number between 0 and 1 in this equation up here. So suppose theta is equal to 1. If theta is equal to 1, then you're at this point right here. Because it's 1 times f of u. Okay. On the other hand, if theta is 0, this term drops out, and this just becomes f of v. That's this point right here. So at this point right here, you have theta equals 0. Right here, you have theta equals 1. Okay. If you're right in the middle, you would be on this midpoint of the line. This would be theta equals 0.5. So everywhere, for all values of theta between 0 and 1, this line has to lie on or below the actual value of the function. This part right here, see, if theta equals 0, or let's say theta equals 1. Theta equals 1, f of u, because this term drops out. 1 minus theta be 0. But if theta equals 0, this term drops out, and this just becomes f of v. So this is just measuring the arc of the function itself as theta goes from 0 to 1, or as it goes from 1 to 0, excuse me. So this is a concave function. Any 2 points you pick, u and v have to be distinct. They have to be different. That's the only requirement. But any 2 points you pick for u and v, you connect a straight line. Connecting those 2 points, the straight line has to lie below the curve. Okay. All right. Now, this particular function, if this holds, f is concave. F is concave. If and only if this condition right here holds. If you replace this weak inequality with a strong inequality, if that holds, then you say f is strictly concave. Okay, f is strictly concave then. Okay, strictly concave. If the inequality goes in the other direction, then it's convex. So the condition for convexity would be this. You would change this to go in the other way. Now, the height of the line segment would have to lie everywhere above the height of the arc. That would be convex. Okay. And if we made this a strong inequality, then it would be strictly convex. So I would have to change this to be strictly convex. Let me draw you some pictures to illustrate these. In this case right here, it looks to me, the way I've drawn it, in the domain that I've shown, that it's strictly concave. Okay. But suppose we considered this function. Suppose a function looks like this, and it has a flat top. This function would be what?
this concave because you could connect 2 points and they wouldn't be under the arc?
Well, in order for it to be concave, the straight line has to be on or below. It could be on. So in that case, this function is it's concave, but not strictly concave. Okay, so this one would be concave because it has a flat top. If you connect any 2 points, then the line segment will lie on or below. Okay, so right here, if I pick 2 points right along this top M and N and connected them with the straight line, the straight line would lie right on function. Yes?
Then for any linear function, would it both be concave and convex?
Exactly right.
Okay.
For a linear function, it would be both concave and concave and convex, but not strictly concave or not strictly convex. Very good, Tyler. That was the next thing I was going to do. You anticipated me. Now, connect any 2 points. The straight. I don't know what this cough just came on me suddenly.
Have some Gatorade. Do you want something like that?
I don't know that Gatorade would help, but thank you. So in this case, the line segment is right on top of the function. So this means it's concave, but not strictly concave. It's also convex, but not strictly convex. A convex function would look like this. Now, connect any 2 points. And the line segment lies everywhere on or above. In this case, it would be strictly convex. But this case here is also convex. Okay. But not strictly convex, obviously. Okay, that's kind of the pictures. So you kind of have the idea now. Let me go through a simple math example where you can determine the concavity or convexity just by the algebraic definition. And I'm going to deliberately choose a simple example because doing these algebraically can get very tricky. So let's consider this function. F of x equals x squared. We want to use this definition right here to determine whether it's concave, convex, strictly concave, strictly convex. By the way, if a function is strictly concave, it's most certainly concave. Okay. If a function is strictly convex, it has to be convex. Okay. But vice versa doesn't hold. Concave is not necessarily strictly concave. Thank you. I'll try to see if this will help. If this doesn't help, then Jacob, I'll try some of your Gatorade. Thank
I
you.
feel like the sugar does help.
You think the sugar helps? Oh, okay, I'll try. Okay, okay. Thank you.
I don't know, it's not me.
Thank you, Ian. All right, let's consider this example here. Now notice, in this case, let's use our definition. What is f of u? Ian, I have to ask you, Were you just concerned about me, or were you just tired of listening to me cough? Or some of both?
I was a bit concerned about you. Your face turned a bit red, and
Okay.
I saw that I was on my grandpa. And I was
Okay, okay.
There's a linear combination probably.
Yeah, with economists, you never can tell. Okay. Thank you, Ian. So what is f of u in this case? Kelsey, I heard you. Oh, I heard you say something. I thought you were giving the answer. Oh, okay. It's not hard. Yes, Tyler. U squared. See, x is equal to u. U is just a value, a certain value of x. So x is equal to u, so it's just u squared. See, whatever this value is, f of 1 would be 1. F of 2 would be 2 squared or 4. So f of u is just u squared. Okay, and Kelsey, what is f of v? V squared. There you go. So those are easy. So if we get the left-hand side of that expression up there is this. Theta times u squared plus 1 minus theta times v squared. Okay. Now, we want to see, my suspicion, by the way, what would your suspicion be if you had to guess at this point whether this function's concave or convex, strictly concave or strictly convex? What would you guess?
Strictly convex.
What's that?
Strictly convex.
Yes, because y equals x squared. What does it look like? Just a parabola, a U-shaped parabola. So your suspicion would be strictly convex. So let's just say that's our hypothesis. If that's true, then we should have this. This should be greater than this. So what is f evaluated at theta u plus 1 minus theta v? This one's a little trickier. What is that equal to? Well, before, when you got f of u, you just said, okay, here's the value for x, so I square it. If it's v, then I square that. So what is the value of x now? It's this. So you just square that whole thing. Okay, so this will be equal to just this, theta u plus 1 minus theta v squared. And what will that be? Well, if you just square this, you'll get theta squared u squared plus you get a 1 minus theta squared v squared plus you'll get 2 theta u times 1 minus theta v. Okay. Just multiply this thing in brackets times itself, and that's what you get. Okay, so we want to, that's f of theta u plus 1 minus theta v, or this term right here. So let me rewrite it down here. We've got our, this side we found is equal to theta times u squared plus 1 minus theta v squared. And the question is that greater than this, which we just found out to be this? And let me rewrite that last term as 2 theta 1 minus theta uv. Lynn, is this coming through? All right. Okay. All right. We want to show that this left-hand side, which is the height of the line segment, is always greater than the height of the arc. So we just do some algebra. Let's pull everything over to the left. Notice we got And I tell you, this is a simple problem. Some of them are much more algebraically challenging than this. Fortunately, we're going to learn some mathematical techniques that will allow us to determine concavity and convexity much more quickly. But I want to first show you this one. Okay, so we bring everything over to the left. So it's theta u squared minus theta squared u squared. Plus 1 minus theta v squared minus, we bring this term over to the left. Okay, and then we just have a minus 2 theta, 1 minus theta uv. And we want to show that that's greater than 0. So what we can do next is we can factor out the u squared and write this as theta times, I'll use brackets here, u squared. No, we want to factor, I'm sorry, we want to factor out the u squared. Let's factor out the u squared. And I'll write this way, theta minus theta squared. Put brackets around that, times the u squared. Put the u squared over here. Okay, so I just factored out the u squared. Do the same thing here, factor out the v squared. And so we can write this as 1 minus theta minus 1 minus theta squared times v squared. Okay. Minus 2 theta, 1 minus theta uv. Okay. And this, we can, from this term, we could factor out a theta and write this as theta times 1 minus theta. See, that would give us our theta here, minus theta squared, times u squared. Notice this term within brackets. This is 1 minus theta minus this.